We're in the middle of the holidays and my stomach is full. Which means we're talking about full joins on today's chapter. The puns aren't getting any easier from here. Of DataBard. DataBard, 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 DataBard. Dabba 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 dabba, hoi hoi hoi. What you're seeing here is an excerpt of a full-day SQL training workshop from the basic fundamentals all the way up to some pretty complicated scenarios in 8 hours. So tell me if you do like this content, because if you do, I do have more that I can make videos on. Let me know in the comments. I'll be sure to make those sorts of things in future videos if you think it'll be helpful. Now that we've got the structure of Lego bricks that gives us the ability to join, how do the joins themselves work? Here's how joins work in a nutshell. First of all, joins are defined by predicates. To be clear, when I'm talking a predicate, I mean this information on the upper right corner of your screen. On a.keyColumns equals b.keyColumns. What's a predicate? Predicate means I take a formula and I can assess whether it's true or false. For example, does the number 2 equal the number 2? I can assess whether that is true or false. 2 equal to 2? That's true. 2 equal to 4? That's false. Okay? So we know that a join requires a predicate. How does it use the predicate? Like the following. When you define a join between two tables, we look at them as A and B in the same way that the Venn diagrams do. So we define the join on a predicate. What actually happens though behind the scenes? Well, we know starting out that table A is going to have so many records, table B is going to have so many records. What happens in a join is all of the records in A get compared to all possible records that exist in B, and we essentially create a logical Cartesian combination of all possibilities of a record in A finding a matching record in B. For all of those combinations, we then assess each combination of records, and we assess for the predicate, does the predicate succeed for the record or does it fail? Depending on the result of that, determines what we get back in our result set. Now, in the shift from a join that has no predicate to a join that has a predicate, an important thing occurs. You remember from the cross join that we essentially get a Cartesian product. Multiply the records of one table with the records of the other table. That is the total number of records you can get back. When we get to joins with predicates, we're no longer dealing with two dimensions and the multiplication. We are shifting to a single dimension, or really a line, where we are trying to join these records once to these records over here once, and depending on what we find, that is what we get. Let's be clear about what I mean about success and failure. What does success and failure mean when we talk about the predicate? Success means we find at least one matching record, which means for a record in A, we find at least one successful record in B. That is considered success. Failure means that a record in A looks in B to find a corresponding record based on the predicate, and it finds no match whatsoever. Now, knowing the definition of success, when we have a record in A successfully join into B, those two records now merge together into one really wide row that has all of the columns in A and all of the columns in B for each success. First tip when you're defining joins is your joins have to be very specific, because it determines how many records you get back. If I have a record in A with a value of 1, and I have two records over here that both have a value of 1, A is now going to get duplicated to create two total records, where the columns in A are duplicated and the columns in B are unique. When I'm working with a client and I have to debug queries, more often than not, the first issue that you have to resolve is identify if your joins are innately creating duplicates by not having predicates that are well defined enough. Once you solve that, more often than not, that solves your duplication issue. So this is logically how joins work. All the possible records in A compared to all the possible records in B. What's the rest of the terms for? I haven't even talked about inners, outers, lefts, rights, and whatnot. What differs and where we then start adding in those words is what we want to do with records that fail the join predicate. That's the only difference between them. Logically, all joins do the exact same thing that I explained. All records in A compared to all records in B. The only difference is, based on that comparison, we return a different set of records from that comparison depending on the predicate and the type of join that we define. Don't believe me? Let me showcase it in a demo. Using a cross join to showcase what happens in the logic of a join, we can now identify the problem and why the other types exist. Having something like this where product subcategories are constantly duplicated because there's no logic here that confirms that this product subcategory actually has any relationship to this product. How do we solve that? We start adding in a predicate and we start changing from a cross join to a join that is more specific. And again, from there, the goal is these 23,000 combinations that we found, we want to reduce those to the combinations we care about in our analysis. Let's take a step down from the cross join to the next type of join that is more specific than the cross join, but only down by a step. We move on to the full join. What is different here is now we have a predicate, and we're testing this predicate to say we only want to find situations where a record on dim product has a product subcategory key of 1, and then we find a record in table B, which is product subcategory, where the product subcategory key also has a value of 1. The numbers match. Now, to be clear, this isn't that the column names have to match. The column names could be anything that they want. What's important is that the information stored in the column for a given record matches between the two tables. Beyond that, these columns could be named anything. Let's go ahead and take our query, and logically it's the same thing as the cross join, other than it's a different type of join, going from cross to full. Let's see how many records we get back. We get back 607 records, significantly fewer than the initial records we started out with. So what are the records that were excluded? To be more specific, what are the combinations that are now ignored? Since we're defining it on a predicate, now it is based on the relationship of the predicate. I'll scroll down a little bit to best showcase this to a point where we've actually got the relationship defined. What we've done now is when we have a product record that has a product subcategory key populated on dim product, if I scroll over here to the right, I should now find that this product subcategory key, which is now coming from the product subcategory table, has the same value. This is a record where the predicate was successful. The value 14 found the value 14. And that's how we know these records have a relationship that belongs. Why do we still have 607 records though? Well, a full join allows the possibility of this. We're going to take a look at our A table. We're going to call that our left table. We're then going to take a look at our B table, product subcategory. We're going to call that our B table. In a full join situation, we're anticipating the possibility of what we've seen here. The records successfully match, 14 equals 14. We're also expecting the possibility that 14 in A might not find a 14 in B. Or to be more specific, if it's like 4,700 in A, and we don't find 4,700 in B, we anticipate that to happen. In a full join, what happens in that case is the record from A is returned at least once, and if it can't find a corresponding value in the right table, it still returns the record, but any of the columns from B are returned as null. Let's scroll back up to the top of our set here, and I'll show you what I mean. Starting with record 2, we can see that product key has a value, but there's no product subcategory key. If I scroll to the right, starting with product subcategory and everything following, there is now null values for everything. This is how you know the join failed. And because the join failed, the full join resolves it in saying, I'm still going to return a record that failed the join, but since I can't figure out what are the values in a corresponding table because the join failed, I'm not going to try and return a value. Instead, I'm going to return null. What's special about full, though, is it goes both ways. If I have a record in A that can't find a corresponding record in B, I return the record from A. If I find a record in B that I check for a record in A and I can't find a corresponding record there either, I still return the record. That is what this first record is about. You can see I've got product subcategory columns populated. Subcategory key, subcategory name, so on and so forth. But as soon as I scroll to the left, the values become null. So in this case, again, product is left, product subcategory is right. Records 2 and following, when product subcategory is null, that is the left side of it. Left product record couldn't find right product subcategory. And the first record is the inverse. Product subcategory has a value and couldn't find a product. We still want to return this too. As I was working on this video in particular, one challenge that I genuinely had with this is, what are valid use cases for actively using full join? And I'll say, to be perfectly honest, in production implementations of things like ETL code or report queries, the situations where I've actually had to write a full join, I can for sure count on one hand, and I'm not sure if I even have to use any fingers to do so. The full join is really weird in comparison to the others because it doesn't necessarily provide the full results of just a singular table. It's sort of providing the full values of two tables, but depends on how your predicate is set. What really is then the use case for a full join? In my mind, debugging is usually the biggest scenario I've had. Suppose you're in a situation where maybe you're trying to compare data between your source environment and your destination environment, and you want to see situations where you're profiling, does the record still exist in source, or does it not exist yet in your destination table via your ETL? There, at least a full join would make it easy within a simple query, and you can compare data from your source system and your target database, and you would be able to focus on the situations where you have a record in source, not in destination, and where you have a record in destination that no longer exists in source. But is that super helpful? Really, for that edge use case? This is where I'm genuinely wanting to ask the community to see if anybody is having value out of using the full join. At least personally, I haven't seen a lot of use cases for it. That's a lot of content for one video, so we're going to cut it here, but we will be covering the other join types in future videos. So that does bring us to the end of this video, and hopefully this is helpful. If so, like, subscribe to the channel, and let everybody know if they're struggling to figure out how joins work, check out this series for some useful tips and Lego analogies. Have any follow-up questions? Hit me up in the comments. I'll do my best to answer my questions there or in future videos. For now, I'm Data Bard, and I'll see you in the next chapter. Today's chapter may be done, but that doesn't mean the story is over. If you are looking to work with someone like me to improve your data strategy or implementation, go to bakertilly.com/digital, fill out the contact form, and let's see how we can help you take the next step on your data journey.